Trigonometry, Chapter 7, Applications of Trigonometry, Vectors, Section 2, The Law of Cosines, Video 5, Using the Law of Cosines to Find Angles. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we used the law of cosines to solve a triangle when the three sides were known, side, side, side. In this video, we summarize the use of the law of cosines for finding angles. Now, in the previous video, we were given triangle ABC. We were given for triangle ABC, side A equals 9.8 feet, side B equals 15.9 feet, and side C equals 21.1 feet. We use the law of cosines to solve for angle A by solving 9.8 squared equals 15.9 squared plus 21.1 squared minus 2 times 15.9 times 21.1 times cosine of A. In this process, we preserved as much precision as possible by not doing any rounding until the end. The only operations that could have required rounding were division and inverse cosine. We did the same thing to find angle B. But anytime you solve a formula repeatedly for specific values, it begs the question as to whether you should solve the formula prior to substituting values. In other words, when we used a squared plus equals, a squared equals b squared plus c squared minus 2bc cosine of A to solve for angle A, we substituted the values, then solved for angle A. Could we first solve for angle A, thus creating a new formula, and then substitute values? The answer is, of course, we can. To solve a squared equals b squared plus c squared minus 2bc cosine A for angle A, we clearly have to get rid of everything that's on the right side with angle A. But let's look at this a little bit more generally. I'm about to unleash some algebraic perspective on this problem, which can serve you well in future issues, future problems for this class or classes beyond it. Now, this equation contains four terms, separated by addition and subtraction. Loosely speaking, a term is a multiplication or division problem, and they are separated by addition and subtraction. So we have four terms, a squared, b squared, c squared, and 2bc cosine A. Now to solve for angle A, we must first isolate its term, the term highlighted in blue, the 2bc cosine angle A. When isolating a term, it is desirable for that term to be positive since we will eventually divide by its coefficient. It's just cleaner to divide by a positive than a negative when you have the option. Now, since this term in blue is negative, we can make it positive by either multiplying both sides of the equation by -1, which would change everybody's signs, or by moving this term to the other side of the equation, which is equivalent to adding the blue term to both sides. But in addition to making this term positive, we also want to isolate it from the other terms. In general, algebraically speaking, to solve for something crammed inside of an equation, the first thing you want to do is isolate its term, and then you want to divide away the coefficient in front of it. Now, to achieve both goals, to make the blue term positive and isolate it from the yellow terms, we can move terms across the equal sign, changing their signs when we do. We do this by moving the a squared term to the right, which will make it negative, and simultaneously moving the 2bc cosine A term to the left. The motivation behind this is I want the thing in blue to be positive, so I'm going to put it on the left, which means everything else needs to go to the right. And when we make this switch, our equation becomes 2bc cosine of A equals b squared plus c squared minus a squared. Gets us closer to solving for A, because now all we have to do is divide both sides by 2bc to isolate cosine of A. That gives us cosine of A equals b squared plus c squared minus a squared over 2bc. Now, we could leave the new version of the law of cosines like this, or if you wanted a formula that explicitly started with A equals, you could take inverse cosine of each sign. So it would say A equals cosine inverse of that mess. But I'm going to leave it like this. And since the choice of variables was irrelevant, we could permute the variables to have any angle inside the cosine. So there's actually three variations of this. One that says cosine A equals, one that says cosine B equals, one that says cosine C equals. And you can see that it would be easy to get these formulas mixed up if you're trying to memorize them all, unless you focused on the structures. So really, we have 6 variations of the law of cosines, 3 of which look like this with 3 different angles, and the other 3 were solved for cosine of that angle. Now, you could also say there's 2 generic versions where OPP is the side opposite the included angle, and adjacent 1 and adjacent 2 are the 2 sides adjacent to the included angle. Here's the original generic version of the law of cosines. Opposite squared equals adjacent squared plus adjacent squared minus 2 times the adjacent side times the cosine of the included angle. Or if we solve that for cosine, it would be cosine of the included angle equals the sum of the squares of the adjacent sides minus the square of the opposite side, all divided by twice the product of the adjacent sides. So what's my point? My point is this. When you're solving a problem, math or otherwise, there's usually more than one way to approach it. As a problem solver, it's your job is to find the approach that works best for you and become proficient at it. Personally, I always just use the original version of the law of cosines, the ones on the left or the one on the top, and solve for the angle when necessary because I'm not afraid of algebra. For example, in triangle DEF, side D equals 10, side E equals 15, and side F equals 18. Find angle F, round to 1 decimal place. It's worth mentioning that these satisfy the triangle inequality. But in triangle DEF, since sides D and E are adjacent to angle F, and side F is opposite of angle F, we're going to let adjacent 1 be 10, adjacent 2 be 15, and opposite equals 15 in the generic formula below. And when we make those substitutions, we get this. Remember, we're finding cosine of angle F, or we're finding angle F. We can evaluate the numerator and denominator separately, and those ended up being 1 over 300. And then cosine inverse of that, we get about 89.8 degrees. So it's actually pretty straightforward once you get to this point. Now you try. Pause this uncharacteristically long video and try the following. In triangle DEF, I have the same 3 sides as before. D is 10, E is 15, F is 18. Find angle D, round to 1 decimal place. Pause the video, give it a try. All right, here's your fair warning if you haven't paused the video to try it yet. Solution in 3, 2, and 1. Since we're finding angle D, sides E and F are adjacent to angle D, and side D is opposite angle D. And so cosine of D is the sum of the squares of the adjacent sides, 15 squared plus 18 squared, minus the square of the opposite side, minus 10 squared, over 2 times the product of the adjacent sides, which gives us 449 in the numerator, 540 in the denominator. And so D is cosine inverse of 449 over 540, which is approximately 33.7 degrees. And just a little side note, because of the same setup as before, we've almost solved this triangle. That's angle D, that's angle F, and of course to find angle E, we could just subtract the 2 angles from 180.